Hi everybody. This lesson is on 1.4, Separable Differential Equations. Okay, a lot of this will be familiar to you because it was covered in Math 70 in Chapter 9. Okay, but we are going to go over it again. So let's do a definition. A first order differential equation is called separable if it can be written in the following form. P of y times dy dx is equal to q of x. So this is what it means to have a separable differential equation. So theorem. The nice thing about separable differential equations is that they have the easiest technique for solving the differential equations. So star above has the general solution. It looks like this. You integrate the p of y function and you integrate the q of x function. And I'm going to put the plus c in here, where c is an arbitrary constant. This must be included in order for it to be the general solution. Okay? Now, informally, well, I'm not going to prove this theorem just because this is actually proven for you guys in Calc 2, and I don't want to waste too much time showing you why something is true that you've already seen before, okay? But informally, we solve a separable differential equation by separating the x's and y's, then integrating both sides. Okay, so remember we had p of y times dy dx is equal to q of x, right? And so the way you want to think about it is, informally, you're going to multiply both sides by dx. If you do that, you get p of y dy is equal to q of x dx, and then you integrate both sides. And that leads us to the general solution, okay? So this is why it's called separable. It's called separable because of this informal process of separating the variables so that you have all the y's on one side and all the x's on the other side. Okay, this is a technique we have to learn. It's the easiest type of differential equation that we're going to see in this class. You've seen it before. And it works for nonlinear differential equations too, but the catch is that it has to be in this form, okay? It has to be a function of y times the derivative and then the function of x by itself. Okay, so let's try an example. So an example here, I want us to solve the differential equation. It's going to be e to the y plus 4y squared times dy dx is equal to 9x e to the x. Okay, so this is our differential equation, and we notice that all of the y's are on one side and all of the x's are on the other. So I'm going to write it this way. So before I write this down, actually, I'm going to multiply both sides by dx. I end up with this. And then I'm going to integrate both sides. Now, integrating the left side is easy. This is just e to the y plus, and then this becomes 4/3 y cubed. The other side is a little trickier because we do need to use integration by parts, okay? So let me go ahead and do this work. Integration by parts. Our u would be 9x and our dv would be e to the x dx. Differentiate this, we get the du is 9 dx. Integrate this, we get the v is e to the x. And then our formula becomes uv minus the integral of v times du. I'm going to write it like this, 9e to the x dx. So if I work that out, I get 9x e to the x minus 9e to the x. Okay, that would be the antiderivative there. And so put this whole thing, right, that is the antiderivative, and so my answer is like this, 9x e to the x minus 9e to the x plus c. This is my solution to the differential equation. Let me make this look a little better because it didn't really look like a 3. There you go. Okay. So it is not that bad. You really just have to brush up on your integration, which, by the way, the rest of this course is going to require heavy use of integration. So if you need to, please make sure that you review integration from Calculus 2. Okay. There is a note that I want to point out here. Whenever you divide by a variable, you might not be thinking about this, but if you divide by y, you are assuming y is not 0. So if you don't consider that case separately, end up missing a potential solution. Don't forget about it. Okay, so we are going to always consider these cases separately. To do that, let me go ahead and show you an example here. So example, solve the differential equation. Y prime is equal to negative 2xy squared. Okay. So it might help to look at it this way. dy dx is equal to negative 2xy squared. Now, is this thing separable? It turns out that it is, but you do need to divide both sides by y squared. So if you multiply both sides by 1 over y squared, you end up with the following. I'm also going to separate the dx and put the dx on the other side. So maybe I'll write it this way. I'm going to multiply both sides by dx over y squared. I get the following. I get y to the negative 2 dy is equal to negative 2x dx. Now, before we forget, okay, as soon as you divide by y squared, we made an assumption, didn't we, that y was not 0. So actually, this is case 1. Everything we're writing here is part of case 1. Y is not 0. Okay, so here we are. We're going to divide both sides by this, and so when you integrate the left side, you get y to the negative 1 over negative 1, so that's negative 1 over y is equal to, and then over here we get negative x squared plus c. Okay, so how would we write this as y equals something? Well, if you multiply both sides by negative 1, you get you get 1 over y is equal to x squared minus c. And then take the reciprocal of both sides, you get y of x is equal to 1 over x squared minus c. So this is our solution. But are we done? Did we find every solution? Well, what about the case where y is 0? So case 2. If y equals 0, does that single function solve the differential equation? Well, yes, because then y prime is 0, and if you plug it into the dE, the differential equation, you get 0 equals 0, so it works. Okay. So how would you write this answer? So all solutions y of x is equal to 1 over x squared minus c, and y of x is equal to 0. These are all solutions to the differential equation. You've got a family of functions plus one extra function that we missed, which is the 0 function. In other words, it's just the trivial function. Why did I have to write this separately? Because there was no way, for example, that my original family could have the 0 function, right? Because we've got a 1 on top, a numerator of 1. There's no way we can get 0 out of that. Okay, but I do want to write out a certain note here. So note, or let me write it this way. Sometimes we redefine constants in order to write different families of solutions as a single family. Okay, so this next example is going to illustrate this. So example, I want us to solve the following differential equation. dy dx is equal to negative 2xy. Okay, So how do we do this? Well, again, this is separable. Okay, it is separable. We are going to have to divide both sides by y. So let me write that down here. We're doing case 1. Y is not 0. So if y is not 0, we divide both sides by y. We get the following. dy over y is equal to negative 2x dx. And then after separating, remember, integrate both sides, you get the following. ln of the absolute value of y is equal to negative x squared plus c. Okay. Now, how do we write this as a function? Okay, so this implies what? If you take e to the power of both sides, you get that the absolute value of y is equal to e to the negative x squared plus c. Okay, what does this equal? Well, I could write it this way, can't I? E to the c times e to the negative x squared. And what can we say about e to the c? Isn't e to the c, doesn't this become any positive constant? It can never be 0 and it can never be negative, but it could be every other positive number, okay? So what I'm going to do is I'm going to call that guy a new constant. We're going to call it d, where d is a positive constant. So here's what we have now. We have the absolute value of y is equal to d e to the negative x squared. So now what does y become? We have the absolute value of y. So doesn't this mean that y is equal to plus or minus d e to the negative x squared? Again, that comes from the absolute value. So this is true where d is positive, right? D has to be positive. In other words, 0 is not an option. Okay, but what about case 2? What if y is equal to 0? Then again, we do get 0 equals 0 in the differential equation. In other words, y equals 0 is also a solution. So here's what I'm going to do. I'm going to take my solution from before and my solution now, and I'm going to combine it into a single solution. So the general solution looks like this. Y of x is equal to a e to the negative x squared, where a is any real number. Now, how have I taken everything above into account? Well, I want you to think about it. If a is positive, then it's taking into account this plus right here. If a is negative, then it's taking into account this negative. And what about if a is 0? If a is 0, then we have y equals 0, and we get this guy as well. So we get everything from this single family that I wrote down. Okay? This is just a nice way of writing the answer. You could write it the other way too, but this is the nicest way of writing the answer. Okay, we're going to do one more example of this before we look into a nice application. So actually, I'm going to do a couple more examples, but we're going to do one involving physics and then another one involving Newton's law of cooling. Okay, so let me go first with the physics application. So example. An object with mass m falls from rest starting at a point near the Earth's surface. Assuming that error resistance is proportional to the velocity of the object determine the subsequent motion. Okay, and as a bonus, what is the terminal velocity? Okay, so in order to answer this question, we do have to remember some things about physics. First, we have Newton's second law of motion. Newton's second law says that the sum of all the forces that are acting on an object, let me write it in vector form. The sum of all the force vectors is equal to an object's mass times its acceleration vector. In other words, the sum of all the force vectors is directly proportional to its acceleration, and the constant of proportionality is its mass. Okay? So this right side here, okay, is going to translate to a second derivative, right? Because the acceleration is the second derivative. So let's begin by creating our variable. Let's let y of t be the distance traveled by the object by the object at time t from when it was released. Okay. So this is our definition, and we're going to consider, so in other words, we're going to consider down to be positive. Okay? So if y is equal to 0 at a particular time, that's only when you just let it go, and then if it equals 1, that means it's fallen 1 meter, and so on. Okay, so t is the time. Okay, so what is ma? ma is actually just m times the second derivative, right? Because we know that the first derivative is velocity and the second derivative is acceleration. So let me actually write that down. Okay, dy dt is equal to the velocity, and then the second derivative is equal to the acceleration, right? We know this. Okay? So we know what the right underlined side here is. This part that we just boxed here, that's this. But we need to figure out what the sum of the forces is. Okay? So let me do this on the next page. Let's say that this is the object, okay? Let's say that this is the object, and it is in free fall. If it's in free fall, there are only two things acting on it. We're going to call one of these guys F sub W. This is the weight. And then also acting against it as it's falling is, we're going to call this let's call this F sub air. This is the air resistance. Okay? This is the only, or these are the only things that are acting on the object as it's falling, okay? So if we're calling down positive, then that means that we can write this. Newton's second law. Remember, Newton's second law is that the sum of all forces is mass times acceleration, right? Is equal to the sum of all the force vectors, right? And so here is what we end up with, right? We know now that this is equal to the weight of the object minus the force due to air resistance. Okay? Well, what is the weight of the object? Those of you that remember your physics, this is just m times g, okay, where g is the gravitational constant. What is the force due to air resistance? The force due to air resistance, well, let's go back to the original problem. The force due to air resistance, it says here, it's proportional to the velocity of the object. So the force due to air resistance is equal to k times dy dt, right? Because it's proportional to the velocity, and dy dt is the velocity. So remember, this is Newton's second law, and so we translate this into, it's going to be an initial value problem, okay? My initial value problem is going to be as follows. M times d2y over dt squared is equal to mg minus k times dy dt. And then y of 0 is equal to 0, right? Because we know that at 0 seconds, when we haven't let the object go yet, or we're just letting it go, it hasn't moved yet, right? So in other words, the distance traveled is 0, and then also because it's going from rest, we know that y prime of 0 has to also be 0 because at the beginning it's motionless. Okay, at the beginning its velocity is 0. So what is this? We know that this is actually a second order IVP, right? This is second order. Because we have a second derivative. We don't know how to solve this thing. But we're going to introduce a trick. Okay, we're going to let v of t equal dy dt, right? That's the velocity. And I want you to see what happens here when we do that. We get the following. So I'm going to replace, that means that this guy is going to become v. And then what does this guy become? Well, doesn't dv dt just become d2y over dt squared? In other words, the first derivative of velocity is the second derivative of position, and so here is what our IVP becomes, because this now becomes dv dt. And so if we go to the next line here, after substituting, the IVP becomes m times dv dt is equal to mg minus k times v. Okay, so this is our equation, and also don't forget that v of 0 is 0. In other words, we have a first order now, and this is going to be one of the tricks that we learn later on, is we were able to do this substitution because of the nature of this differential equation. So this is what we have, and notice that this is separable. This is separable, okay? So how do we solve this? Well, if we divide both sides by mg minus kv, we get the following. M over mg minus kv dv is equal to dt. I'm going to integrate both sides here. So what do we end up with? Okay, what's the integral of the left side? Well, remember, everything here is just a constant. The same way that we integrate something like 1 over 1 minus 5x. When you integrate something like this, it would be the natural log, but then you divide it by the slope of the x. So it would be negative 1/5 natural log of 1 minus 5x. So we can use the exact same thing here, okay? This would be m over negative k times the natural log of the absolute value of mg minus kv. And on the right side, we just have a t. Okay? And we also have plus c. Okay, now of course, we're going to find the c, and we can do that by using the initial condition. Okay? So if we know that v of 0 is equal to 0, we get the following. We get 0 is equal to v of 0. So let me write it this way. So you plug in t equals 0 and v equals 0. And what do you end up with here? Okay, you end up with m over negative k times the natural log of mg is equal to c. Right? Because I just plugged in 0 for v and 0 for t in the above. And so, what does this mean? This means that, well, I replace this, my c right here, with that, and I end up with the following. M over negative k times the natural log of mg minus kv is equal to t minus m over k ln of mg. You notice I don't need the absolute value around mg because mass is positive and g is positive, so there is no chance of that being negative. So I drop the absolute value. Okay. Where do I go from here? Well, to go from here, I need to isolate the v, and then once I isolate the v, I'm actually going to be able to solve this. Okay? So what I'm going to do is I'm going to multiply both sides here by the reciprocal of what's next to the natural log. In other words, I'm going to multiply it by negative k over m. So if I multiply both sides of this equation by negative k over m, I end up with the natural log of mg minus kv is equal to negative k over m t plus ln of mg. Okay. What do I get from here? From here, I'm clearly going to get two things, right? Well, actually, sorry, let me go ahead and do e to the power of both sides, okay? So if I do e to the power of both sides, let me do that for the next part here. I'm going to do e to the power of this and e to the power of that. So what I end up with is the e and the ln cancel each other out, and so we end up with the absolute value of mg minus kv is equal to, let's see, what do we get here? We get mg times e to the negative k over mt. Where do I get this from? Look behind, okay? If I raise e to the power of this ln of mg, so I'm using the product rule. The right side is e to the first guy times e to the second guy, but e to the ln of mg is just mg. So that's why I threw it as an mg in front. So this is what we get. Okay, now understand that an absolute value causes two possibilities. Either we get mg minus kv is equal to positive mg e to the negative k over mt, or mg minus kv is equal to negative mg e to the negative k over mt. Okay. Now, remember the initial condition, okay? If you plug in t equals 0 and v equals 0, right, that's the initial condition, you will notice that this devolves into mg equals negative mg. In other words, this minus sign can't be there, okay? The initial condition fails. And so we're going to work with the left side now. We know the right side is impossible. So what do we get from here? Let's move the kv to the other side. Kv, therefore, is equal to mg minus mg e to the negative k over mt. And then divide both sides by k. We get v is equal to, I'll write it this way, mg over k minus mg over k e to the negative k over mt. Now what? Well, let's remember our substitution. So recall, we made a substitution earlier that dy dt is actually equal to v. In other words, now replace it back. And so you end up with dy dt is equal to that thing, or can't I write it this way? And then I'm going to integrate both sides. So what did I do? I just separated variables. Okay, so I turned it into a separable differential equation. So if I integrate the left side, I get y. And what do I get when I integrate the right side? Oh, there is one thing I forgot here. This is our differential equation, but understand that we do have another initial condition, right? Y of 0 is equal to 0. So this is our IVP that we're solving now, okay? I should have said that first. So if I integrate the right side, this just becomes mg over k is a constant, so it's just mg over k times t. How do I integrate the right side? Remember, the integral of e to the something is just e to that thing, except we're going to divide by that slope out in front. So what do I get? I'm going to multiply by the reciprocal. I get times negative m over k. So it's going to be minus mg over k times negative m over k, and then e to the negative k over mt. And then I'm going to write plus d because we do have a different constant here. Okay? So what does this become? This actually becomes y equals mg over k t plus m squared g over k squared, and then e to the negative k over mt, and then plus d. So now let's use our initial condition to find d. We know that y of 0 is equal to 0. So if you plug that in on both sides, you end up with, so y of 0 equals 0 gives us 0 equals d minus m squared over k squared g. Because look back. 0 equals, right, because this is a t, sorry, let me make that more clear. This is a t, so when you plug in 0, that term goes away, and then everything goes away over here except for So you end up with 0 is equal to, if you plug in 0 for t, you end up with just m squared g over k squared plus d. Okay? All right. So then, so I think, yeah, sorry, I actually got my sign wrong on the other part. Yeah, there should be a plus here. Okay, so this means that d is equal to minus m squared over k squared g. So plug that back into my differential equation and I get the following. Y of t is equal to mg over k times t plus m squared over k squared g e to the negative k over m t, and then minus m squared over k squared g, right? Because I took this guy and I plugged it back in for d right here. Okay, so this is my motion, this is my solution to the differential equation. So I answered the first part. So now let's go for the bonus question. The bonus question asks us what the terminal velocity was, right? Terminal velocity is always defined as the limit as n goes to infinity of the velocity. Okay? So what is the velocity? Well, let's come back here, right? The velocity was this, right? Isn't that the velocity? So we're going to take the limit as t goes to infinity of that. So the limit as t goes to infinity of mg minus mg e to the negative k over mt all over k. But as you send t to infinity, this guy goes to 0, right? Because e to the negative infinity is like 1 over infinity, which goes to 0. And so the answer is mg over k. So this is how you find the terminal velocity. It's a neat problem, and this trick where we substituted, let me go back a little bit. The reason why this trick worked is that we had no t's floating around in the original differential equation, and we only had dy dt and the second derivative, and that's why this substitution trick worked. We're going to learn more about this trick later on in this class, okay? But for now, just understand that this is the trick that we used to solve this differential equation. Okay, I also want to go over one more type of problem that we might see, which is Newton's law of cooling. Okay, so what is Newton's law of cooling? Let me write this down right here. Newton's law of cooling says that the rate at which a temperature of an object changes is directly proportional to the difference in the object's temperature and its surrounding temperature. So Ts is equal to the surrounding temperature, and it is a constant, okay? Now note, this is not going to be that difficult. We just have to set things up properly because this is a separable differential equation. So note this leads to a separable initial value problem, so we can find its unique solution. Okay, so I'm going to do an example. A bottle of Chimay Blue is stored at room temperature. Which is 72 degrees Fahrenheit. The inside of your refrigerator is set to 38 degrees Fahrenheit. On the bottle, it says it tastes best at 45 degrees Fahrenheit. Okay? So, you put the bottle in the fridge. And after 15 minutes, the beers, well, let me write it this way. The temperature of the beer is 60 degrees Fahrenheit. How long total will the Chimay Blue need to sit in the fridge in order to reach its ideal temperature? This is a cool problem that I created, based on a beer that I actually really enjoy, bottle of Chimay Blue. So I actually looked up these numbers, and this is the actual temperature that is ideal to consume Chimay Blue. Okay, so let's try this problem, and on the next page we'll start this. So we're going to always start by creating your function. Let's let T of t be the temperature after t minutes. Okay, we're saying t minutes after putting it in the fridge, of course, right? So what does Newton's law of cooling say? It says that dt is equal to negative k times t minus 38, right? Because when you put it in the fridge, the surrounding temperature is 38 degrees. And we also know the following facts. T of 0 is equal to 72, and T of 15 is equal to 60. So we're going to need to use those initial conditions later. And the reason we are given two initial conditions here is because we're going to use one of them to find k. So how do we solve something like this? Well, the trick is to notice that this is separable. As we mentioned before, these problems always work that way. Okay, so I'm going to separate the variables. I'm going to write it this way. dt over t minus 38 is equal to negative k. Sorry, I almost made a mistake here. This should be capital T, right? D capital T equals negative k d little t, right? Let's be careful. Little t is time, capital T is temperature, right? So we're going to do this, and then we're going to integrate both sides. So if we do that, we get natural log of t minus 38 is equal to negative kt plus c. Now we're going to plug in the initial conditions, and let's start by plugging in t of 0. So we know that t of 0 is equal to 72, right? So if we plug in condition 1, let's call this condition 1, and let's call this guy condition 2. So condition 1 gives us the following. I plug in 72 for t, so we end up with the natural log of, let's see, 72 minus 38 is 34, right? So it's going to be the natural log of 34. I don't need absolute value anymore because that's a positive number, is equal to, k is 0, you just get c. So what does this mean? This means that the natural log of t minus 38 is equal to negative kt plus the natural log of 34. Okay? So we could take the natural log, we did that just now. And so what we're going to do now is we're going to find k, and we're going to find k by plugging in condition 2. So what does condition 2 say? It says the natural log of, now I'm going to plug in 60, right? So it says the natural log of, what's 60 minus 38? That is 22, right? The natural log of 22 is equal to, if I plug in 15 minutes, it's going to be negative 15k plus the natural log of 34. So we could find k here, can't we? Okay, so if I move stuff around, I get the following. I get 15k is equal to ln of 34 minus ln of 22. Or this is really the natural log of 34 over 22, right? Using rule of logs. And so if I solve for k, k is equal to 1/15 natural log of 34 over 22. So that's k. So all of this now, I have to replace this k in here with that. Okay, and rewrite that equation. So let's rewrite it on the next line. This means that the natural log of t minus 38 is equal to negative t over 15 ln of 34 over 22 plus ln of 34. Okay, so this is my differential equation solution. It's a very particular solution, right? So what are we trying to figure out? We're trying to figure out for what t does capital T equal. Remember, we want the ideal temperature, so we want to know when capital T is going to be 45. Right? That's what we're trying to answer here. So let's go ahead and plug in 45. We get the natural log of 45 minus 38 is 7. is equal to, I'm just going to write this down, negative t over 15, the natural log of 34 over 22, plus the natural log of 34. So now we just have to solve for t. I'm going to move this guy to the other side. I get t over 15 natural log of 34 over 22. And this is going to equal the natural log of 34 over 7. Okay, what I really did is I moved this guy to the other side, and I moved all of this to this side. And then I combined the ln of 34 minus the ln of 7, okay? Okay, I'm almost done here. What would t equal? I'm going to multiply by the reciprocal of what's next to t. I get the following. 15 ln of 34 sevenths divided by ln of 34 over 22. So this is my exact answer. So this is the number of minutes. But if you put that into a calculator, you will get 54.5 minutes. So this is the amount of time that it will take to reach the ideal temperature in the fridge. In other words, this is a very slow refrigerator, but that is how you do the problem. Thanks very much for watching, guys. That concludes this video.